Okay, let's dive right into this. Today, we're taking the ultimate field trip into the absolute most extreme, mind-bending objects in the universe, black holes. We're going to explore what actually happens when you cross that ultimate point of no return, and we're going to use the real math and physics that govern our cosmos to do it. You know, if the whole concept of a black hole completely bends your brain, don't worry, you're actually in really good company. Back in the 1600s, Isaac Newton famously described gravity as masses attracting each other. But even he found his own theory deeply troubling. I mean, he thought the idea of objects pulling on each other invisibly across vast distances of empty space was just utterly absurd. He knew that it happened, but he couldn't for the life of him explain how. Well, it took hundreds of years to figure out that how, and the math revealed something pretty terrifying. Mathematically speaking, literally anything can become a black hole. If you took Mount Everest and somehow compressed it into a space smaller than a single nanometer, its density would become so unimaginably huge that its gravitational pull would trap even light. You could do the exact same thing by compressing the entire Earth down to the size of a peanut. Even you or I could become a black hole if we were squeezed tightly enough. We call this magical little boundary the Schwarzschild's radius. When a massive star runs out of fuel, it can't support its own weight anymore, and it collapses down into this radius. All that mass just gets crushed into a single, infinitesimally small point called a singularity. The density becomes infinite, and the gravitational pull is so extreme that it violently contorts reality itself. And this brilliantly illustrates the massive leap Albert Einstein made with his general theory of relativity. Einstein finally solved Newton's problem of action at a distance. He realized that objects don't exert forces on each other directly through empty space. Instead, a massive object actually curves and warps the fabric of space-time around it, so things fall toward a black hole simply because they're following the severe curve of the space-time they happen to be traveling through. Unlocking this bizarre reality was, honestly, a grueling process. Einstein published his incredibly complex field equations in 1915. Just a year later, Carl Schwarzschild, who was actually stationed on the front lines of World War I at the time, found the first solution proving black holes were mathematically possible. But scientists thought they were just too preposterous to exist in the real world. It wasn't until 1939 that J. Robert Oppenheimer proved massive stars actually do collapse indefinitely. And incredibly, it took all the way until 1963 for Roy Kerr to solve the math for a black hole that's spinning. Part 1. The approach, the outside perspective. So, now that we've got the math, let's start our spatial field trip. Imagine we're safely approaching a black hole in a spaceship. What exactly are we going to see? Well, because the black hole is violently warping spacetime, it acts like a massive cosmic magnifying glass. Light traveling from galaxies millions of light years behind the black hole gets contorted and twisted around it. This produces these massive visual smears, smudges, and glowing rings. It's known as gravitational lensing, and it basically turns a backdrop of the universe into a warped funhouse mirror. As we fly even closer, a larger and larger chunk of our view is just swallowed by pure darkness. Right at the edge of this darkness, we hit a fascinating boundary called the photon sphere. Here, gravity is so perfectly balanced that particles of light, photons, don't get sucked in, but they don't escape either. They literally orbit the black hole. Which means if you stopped right here and looked directly to your side, you could theoretically see the back of your own head, because the light reflecting off your hair would travel all the way around the black hole and right back into your eyes. Crazy, right? Now, what if you stayed a safe distance away and watched me jump in? Because extreme gravity warps time just as much as space, our perspectives would completely shatter. From your point of view, safely outside, you'd never actually see me fall in. You would see me slow down, freeze, and slowly fade to red as my light shifts. My time would appear to completely stop. But for me, the falling traveler, my time feels completely normal. I'd plunge right past the boundary without even noticing a bump, heading straight toward my doom. Part 2, the plunge. Crossing the event horizon. This brings us to the most famous boundary in astrophysics, the ultimate point of no return. But what is physically happening to space here? A great way to visualize this mathematical threshold is to imagine space itself behaving like a waterfall. As you approach the black hole, the river of space flows inwards faster and faster. Photons of light are like fish trying to swim upstream against this massive flow. Right at the event horizon, the space is falling inward at the exact speed of light. And once you're inside the horizon, space is plunging toward the singularity faster than the speed of light. Literally nothing can swim faster enough to escape. And as you fall deeper, Well, the physical reality gets pretty grim. The gravitational pull becomes so intensely concentrated that the difference in gravity across just a few feet is massive. The parts of your body closer to the center are pulled vastly stronger than the parts facing away. Your molecules are violently stretched toward the singularity. Scientists actually call this highly technical, terrifying process spaghettification. Literally, you become spaghetti. Part 3. Inside the spinning singularity, the Kerr solution. Now, in a simple, static black hole, you hit the center and die. But real stars rotate, so when they collapse, they have to conserve that angular momentum, meaning real black holes rotate too. Let's move to and see how this builds into something truly majestic. A spinning black hole has layers. First, you have the ergosphere, where space is literally dragged around the black hole faster than light. Then, the outer horizon, your standard point of no return. But if you somehow survive the plunge, you reach an inner horizon. Inside here, the math says you can suddenly move around freely again, and the singularity isn't a single point anymore. The spin stretches it out into a massive swirling ring. Because it's a ring, it's theoretically possible to fly right through the center of the singularity without ever hitting it. And this is where things get truly wild. We are about to dive down the ultimate sci-fi rabbit hole of theoretical physics. Part 4. The Mathematical Beyond. Exploring the maximal extension. Physicists use these incredible visual tools called Penrose diagrams to map the infinite future, the infinite past, and the flow of light in curved spacetime. And when they push these diagrams to their absolute limits, they find some startling predictions. You see, general relativity doesn't actually dictate which way time has to flow. The math works perfectly well backwards. If you reverse the equations of a black hole, you get its exact opposite, a white hole. Instead of an event horizon that traps you forever, a white hole has a horizon that aggressively, violently ejects matter and light outward. Nothing in the universe can ever go inside a white hole. When physicists stitched the mathematical shapes of these black holes and white holes together, they found they connect at a point in space-time. This connection is called an Einstein-Rosen bridge, though you probably know it as a wormhole. The math heavily implies that the black hole in our universe could act as a tunnel, connecting us directly to a white hole in an entirely separate, parallel universe. So if we follow the equations literally, here is your ultimate science fiction voyage. You dive into a rotating black hole in our universe. You carefully fly through the center of that ring singularity. You're instantly funneled into a white hole, which violently blasts you out into a brand new parallel universe. Or if you turn a different way, maybe into an antiverse where gravity pushes instead of pulls, the math allows for an infinite chain of these universes. It's absolutely mind-blowing. Part 5. Math versus reality. The grounding resolution. Okay, before we pack our bags for the antiverse, we need to take a step back. So the crucial point is, mathematical possibility doesn't always equal physical reality. A lot of this relies on these eternal black hole models sitting in perfectly empty universes, which just isn't how our messy universe actually works. Here's the fatal flaw for our immortal astronaut. In a spinning black hole, as you approach that inner horizon, you're essentially looking at the entire infinite timeline of the outside universe compressed into a single moment. All the light and energy that will ever fall into the black hole piles up at this boundary at exactly the same time. This creates a literal wall of infinite energy that births a brand new singularity, completely sealing off the ring and destroying any path to another universe. Well, what about just building a stable wormhole? While Kip Thorne and others found geometries in Einstein's equations that allow for stable interstellar highways, there's a massive catch. To keep a wormhole open and prevent it from instantly pinching shut, you'd need to fill it with exotic matter that literally has a negative energy density. And as far as we know, this directly violates the actual laws of physical matter in our universe. So, traversable wormholes and white holes likely don't exist. But scientists are still finding ingenious ways to test these boundaries. For example, researchers build acoustic black holes in labs. Yes, they're actually called dumb holes, using fluids moving at the speed of sound to trap acoustic waves. It lets us study horizon physics safely right here on Earth. And remember, less than a century ago, the brightest minds in physics thought black holes were completely preposterous too. Science loves a surprise. I want to leave you with this final thought. The cosmological principle states that because the universe is expanding uniformly everywhere at once, no matter where you are scientifically the exact center of the observable universe. We are each standing at the center of a cosmos filled with bending light, warped time, and bottomless mathematical mysteries. So what mind-bending reality will we map out next? Thanks for joining me on this explainer. Keep looking up and stay curious.